Hello, and welcome to our discussion of a Fourier cosine series example. We are going to compute the Fourier cosine series of f of x equals sine of x on the interval 0 to pi. So we begin by looking at what we need to compute. We need the Fourier cosine coefficients. These are big AK of f equals 2 divided by pi times the integral from 0 to pi of sine of x times cosine of k pi x over pi. Here our period is going to be p equals pi. And so this simplifies a little to 2 over pi times the integral from 0 to pi sine of x cosine of kx. And perhaps the first natural thing to do is to anti-differentiate. Let's take the indefinite integral of sine of x times cosine of kx. And that turns out to be 1/2 times the quantity cosine of k minus 1x over k minus 1 minus cosine of k plus 1x over k plus 1. Now how you do this is up to you. You could do an integration by parts and maybe a little u substitution. You could go to a symbolic calculator and get it out and simplify it. However you get it, this is the antiderivative of sine of x times cosine of kx. And we look at this a little more carefully now, and we immediately see we're going to have to do the case k equals 1 separately. Because if I try to use this formula on k equals 1, I will have a division by 0 in that 1 over k minus 1 factor. So I'll handle k equals 1 separately. For now, let's evaluate this integral at k not equal to 1. So we get 2 over pi times the integral from 0 to pi sine of x cosine of kx. Well, the 2 in the numerator will cancel with my factor of 1/2 from the antiderivative. So that becomes a 1 over pi. And then I plug in x equals pi in the first cosine. So that becomes minus 1 to the power k minus 1. I subtract from that cosine of k plus 1 pi. So that becomes minus 1 to the power k plus 1 over my appropriate k plus 1 denominator. And then I plug in 0 and subtract. So I have cosine of 0 over k minus 1. That gives me a minus 1 over k minus 1. And then I'm subtracting a minus cosine of 0 over k plus 1. That gives me a plus 1 over k plus 1. And so now I basically have the Fourier cosine coefficients. I just have to simplify this expression a little more nicely depending on what k is. And one thing I could do would be to put this all over a common denominator. That wouldn't be too hard. Instead, what I'd rather do is consider the cases of k even and k odd separately. So first, if k is even, then k plus 1 is odd and k minus 1 is odd. And so this tells me that my expression in brackets becomes the following. So my first term, I have a minus 1 to the k minus 1, and k minus 1 is odd, so that gives me a minus 1 over k minus 1. My second term, I'm subtracting minus 1 to the k plus 1, so k plus 1 is odd. That means that minus 1 to the k plus 1 is minus 1. I subtract, so I'll get a plus 1 over k plus 1. And then I don't have to do anything else with my other two terms. I have a minus 1 over k minus 1 and my plus 1 over k plus 1. So this turns into 2 times 1 over k plus 1 minus 1 over k minus 1. And that's equal to 4 over 1 minus k squared once I put it over a common denominator. This is, I think, what very often happens with Fourier series in general. We know the definition of the coefficients, we evaluate the integral, and then we spend a lot of time just trying to make the answer look nice and pretty and simple. So 4 over 1 minus k squared is much cleaner than the expression we started with, and I like it much more. Now, this means that the Fourier cosine coefficient big AK of f is 4 over pi times 1 minus k squared for k even. Remember I had that factor of 1 over pi from the previous slide. And now I can go to k odd. So if k is odd, then k plus 1 and k minus 1 are even, and so this tells me that my big expression from before turns into the following. Let's look at the first term. I have minus 1 to the k minus 1. K minus 1 is even, so that becomes a 1 over k minus 1. I'm subtracting minus 1 to the k plus 1. K plus 1 is even, so I'm subtracting 1 over k plus 1. And then my last two terms, minus 1 over k minus 1 and 1 over k plus 1, stay the same. Now something nice happens. I have a 1 over k minus 1 and a minus 1 over k minus 1. They cancel. I have a minus 1 over k plus 1 and a 1 over k plus 1. They cancel. So I squeezed in my equals 0 here. And so what does this say? If k is odd and k is not equal to 1, then the Fourier cosine coefficient for f is equal to 0. Obviously, in what I've done here, I can't do it automatically for k equals 1 because then I'd be dividing by 0. So the last thing for me to do is to evaluate the k equals 1 Fourier cosine coefficient. So big A1 on f is 2 over pi, integral from 0 to pi, sine of x cosine of x, and that is going to be 2 over pi sine squared of x over 2 from x equals 0 to x equals pi. So I just did a quick u substitution in my head there, or went to a symbolic calculator. And what does this turn out to be? Just 0, because sine at pi and sine at 0 are both 0. So altogether, I see that my Fourier cosine coefficient big A k on f is 0 for all k odd and 4 over pi times 1 minus k squared for k even. In particular, the coefficient is still 0 at k equals 1. I just had to do that calculation in a different way from my previous big formula. And I look at my formula just for a quick check. I see I have no problems with the division in that k even. 1 minus k squared will never be 0 for k even, because that would otherwise require k to be equal to plus or minus 1. Okay, now I can put together my Fourier cosine series for f. This is big A0 on f over 2, plus the sum from k equals 1 to infinity, big AK on f cosine of kx, because here I was taking p equal to pi, so the pi's divide out. And this becomes 2 over pi, plus the sum from k equals 1 to infinity. Here I'm doing a little sleight of hand. I'm only going to consider the even numbered big A's, so I'll sum from k equals 1 to infinity on big A 2k of f cosine of 2kx, because if k were odd, I wouldn't have to consider that term at all. And so this is equal to 2 over pi plus the sum from k equals 1 to infinity of 4 divided by pi times 1 minus 2k squared cosine of 2kx. And I can simplify that a little further as 2 over pi plus 4 over pi times the sum k equals 1 to infinity 1 over 1 minus 4k squared cosine of 2kx. Again, I'm still summing from k equals 1 to infinity, but I had reindexed, so I'm only looking at the a2k's and cosine of 2k's, so the integers inside the sum are all even. And that is my Fourier cosine series for sine of x on the interval 0 to pi.